Hey folks, as a bit of a follow-up to the kinematics video, I wanted to actually record a video showing you how these graphs get made for kinematics and how I can kind of prove to you that the relationships are the way they say they are. So what you're looking at here is a track that's tilted. There's a spring attached at the top, and what we're going to do is use LoggerPro to generate graphs of an oscillating spring. Now, it's possible to do this with a vertically oscillating spring. I just happen to have all the equipment here for this track, and so I decided to make it an angle. And so all of the equations should pop out the same shape. And so the thing that you're going to be watching, I'll try and stay out of the way here, is this event right here. Now, there's like plenty of friction between the wheels of the cart and the track itself, and so this oscillation kind of fizzles out after a while, but it does give a really good view of the graphs. And so what I'm going to do is I'm going to do that, and we're also going to look at the graphs get made kind of live. Now, I really hoped this worked out. I can move this here so you can see. I don't know how well that's going to show up, but it should be okay. And I'm going to have all that show up there. And if this is a bust, then I'll record this again with other things going on. Okay, so what I'm going to do is I'm actually going to set this oscillating, because the first down and up motion is pretty chaotic from what I've seen. So I'm going to let this go down and come back up, and then I'm going to hit play or hit collect on the LoggerPro, and we'll see the graph get made. So here we go. Okay, so I'll watch that video later and see if it's good, and if you're watching it, then it was good. So I can auto scale the graphs, so now they should take up, they don't, they should take up the same time, but they don't. That, and that, and there we go. No, that didn't work. Auto scale. Okay, so now all the graphs take up the same amount of space. So let's take a closer look at the graphs. I realize the silliness of having you look at a computer screen that's not shared, but I didn't have LoggerPro on my personal computer, so that's what you're looking at. And I'm having trouble orienting myself in reality. Hey, there we go. All right, sorry for the rough ride. Okay, on the top of this, you have the position graph. And so this is literally how far away the cart is from the motion detector. You can see this flat line here. There is a point in which the cart gets so close to the motion detector, the motion detector can't reliably read the location. So it kind of flatlines, but then they show up as nice curves there. One thing you'll notice that's different from the video is this position versus time graph doesn't cross zero, because it's a motion detector. There's no such thing as a negative position for a motion detector. So it still has the same shape. And if you analyze the peaks and the troughs of this graph, this is the greatest positive displacement. This is the smallest positive displacement. If you average these two values, you would get the equilibrium position. So this is 0.7, a little over 0.7, this is a little under 0.3. The equilibrium position is probably about half a meter. So that's the equilibrium length of the spring for this oscillation. Okay, so the velocity graph is out of phase with the position graph. The velocity is 0 at those extreme points. So when the cart gets to the either end of its oscillation, it's essentially stopped, and so the velocity is the smallest. But when that cart is passing through its approximate equilibrium location, the speed is the greatest, either negative or positive for that. For acceleration, when the object gets to its extremes, that's when the highest or lowest acceleration should happen. Now you'll see there's a ton of noise in the acceleration graph. Just a reminder that in terms of a motion detector, this is the closest that you get to raw data, the position. Velocity data is calculated off of essentially time data, and then acceleration data is calculated off of velocity data. So little variations in this graph create big noise in the acceleration graph, which is why you see these like random spikes. On the other hand, the force sensor is super like clean looking because it's just raw data from like the flexing of the thing inside the force sensor. So notice that the acceleration and force graphs have exactly the same shape, so they're perfectly in phase. And then the force and position graphs are exactly out of phase. And so when there's a maximum position, there's a minimum of force. Minimum position, maximum force. Now what you have to understand for this one is these troughs of this graph, that's when the cart is the closest to the detector. And so that's when the spring was stretched the maximum possible amount. And so that's when the force was the highest. When the cart gets up to its highest position, the spring, because of how it's made, is essentially completely unstretched. And so we get a minimum force. So all the relationships are in here. These are, again, some of the toughest things to like process if you haven't done trig and calculus yet, which is most of you. So if you have questions, please ask for help. Thanks.